All right, so again, it's a Saturday night and there is an OSU football game, so there's probably going to be some yelling at some point, but finals are coming up and I need to study, and this is a really good way of learning algebra. So, what are we going to learn? Okay, so we talked about ideals when you take localization, or not necessarily localization, but just looking at rings of fractions. And when you look at the ring of fractions, ideals are just what happens, are just things of the form S inverse A, where A are ideals in the ring that you start with. But it turns out the same thing happens for primes almost. There's one catch. So the prime ideals, proper prime ideals of S inverse A are of the form S inverse P, where P is a proper prime ideal of A such that its intersection with S is empty. And that's because, remember we proved something about that last time. If you take, well actually, I guess this statement here, P intersect S is empty, is a little bit superfluous, because if well, no, it's not, because if P intersect S is non-empty, then S inverse P is all of S inverse A, because it has an inverse, and the inverse is given by, well, whatever's in here, you just take 1 over that thing. And so that's how you get the entire ring. So, and you do need this, because just because P is proper in A does not automatically mean that S inverse P is proper in S inverse A. You do need this extra condition here. So anyways, so we've talked, okay, so let's prove this. So what we're going to prove is that if you have an ideal in S inverse A, then it looks like this. And then we need to prove that if you have an ideal S inverse P, well, we know already that that's going to give us an ideal, but we need to prove that the ideal that gives us is going to be prime. So this isn't like the other condition where we just took an ideal. There's a little more work to do here. So anyways, so by the previous result, we know that if you take a proper prime ideal Q of S inverse A, then it's of the form S inverse P, where P is just some ideal in A, and it's given by JS inverse of Q. So we have this natural map here that goes from A to S inverse A, and you just pull back your ideal Q. And we talked about already how when you pull back an ideal, you get an ideal. But in fact, more happens. If you pull back a prime ideal, you get a prime ideal. And that's something that you get, that we talked about like a long time ago. But anyways, so yeah, so that's good. So clearly P is not all of A, because if P were all of A, then S inverse P would be S inverse A, which means that Q would be all of S inverse A, which we've assumed is not the case. Okay, so P is a proper ideal. So we know it's prime, we know it's proper, we need to prove this thing. So again, like I said, if this is not empty, then S inverse P is all of S inverse A. And that again says that Q is S inverse A, which is a contradiction, and so therefore it must be the case that this intersection is empty. Okay, so that's one thing that we had to prove. Now we have to consider every ideal of the form S inverse P, where P is prime, and prove that that gives us a prime ideal in S inverse A. So suppose that you have a proper prime ideal of A, and suppose that its intersection with S is empty. We want to prove that S inverse P, well, it is an ideal. We've proven that already, but we need to prove that it's a prime ideal. So suppose you have two elements in S inverse A such that their product is in S inverse P. We then to confirm primeness, we want to prove that one of these two fractions is in S inverse P. Okay? So if you look at AB over 1, that's just ST over 1 times AB over ST because you cancel the STs. And this is in S inverse P because we know that this product is that which is in S inverse P. And since S inverse P, we know it to be an ideal, so multiplying by an arbitrary element of S inverse A remains us in the ideal S inverse P. So this whole thing is in S inverse P, so A over B is in S inverse P. But if you look back to how we defined S inverse P, this implies that A over B must be an element of P. So that's good, but we know that P is prime. And so then, since P is prime, either A is in P or B is in P. And if A is in P, then A over S is in S inverse P. And if B is in P, then B over T is in S inverse P. So one of these two things is in S inverse P, and that's what we wanted to prove to confirm primeness. And so therefore S inverse P is prime in S inverse A, and that finishes up the proof. All right, so that's that. And now for something completely different. So suppose we have A modules, M and N, and we have an A linear map from M to N. Remember, these are the homomorphisms between modules, or the morphisms between modules, some category theory thing. So we get a natural S inverse A linear map that we'll call it S inverse F, and it goes from S inverse M to S inverse N. And, well, it's given by S inverse F. You just apply it to a fraction, and you just take F and apply it in the numerator. And so you got to be careful here. Something should, like, kind of, a red flag should go off, because, let's see, when I first wrote this down, I was like, oh yeah, well, that makes sense. But M over S here. Remember, these are elements of S inverse M, so these are equivalence classes. So we need to prove that this thing is actually a map. So to prove it's well defined, suppose that you have M over S being equivalent to N over T. This means that there is some S prime such that S prime Tm minus Sn equals 0. And again, remember here for this term here, the T and the S we put on the left. Well, I guess we don't need to because these are abelian. These are commutative rings, and so left ideals and right ideals have the same structure. So we don't really worry too much about whether these ideals are, no, modules. We don't worry too much about whether these modules are left modules or right modules, but I like to think of everything as being left modules. So here we're multiplying on the left by the elements of the ring, and so the thing on the right is the element of the module. Okay, so, and of course the S inverse is on the left as well. Okay, so there's an S prime that makes this happen. So then, I'm missing something here. So I guess this isn't really, okay, no, this works, because this is equal to f of 0. This is what I should have done. I should have multiplied on the left and right by, or basically take this equation and send both the left and the right hand sides through f. And we know that f is an A linear map, so f of 0 is 0. And using a linearity, I broke it up into 2 steps. You could do it in 3 steps. Basically, what you do with this f is by linearity, not the word bilinearity, B-I-L-I-N-E-A-R, but because of linearity, you can take this s prime out front and you get this. And now because this is a, well, have we proven that this is a group homomorphism under addition? Well, it obviously is, because it is under in the numerator. That's something that I'm not going to go ahead and prove, but you can prove it. But anyways, if you look at what happens here, you can bring this as, this is just f of Tm minus f of Sn. Oh wait, no, we know that's the case because we know that f is alinear. Yeah, what am I talking about? Okay, so yeah, because f is alinear, f is a homomorphism, so you can bring in, so this is f of tm minus f of Sn, and if you bring the t out front and then the s out front, you get tfm minus sfn. And if you look at this equation, this being equal to 0 means that this over this is equivalent to this over this, i.e. f over s is equivalent to f over fn over t. So if these two things are equivalent, then note that these two things, these are the images of these two things under this map. And so if these two things are equivalent, then so are these things, and so it is a well-defined map. All right, so there's that. Now, we have one more proposition here. How am I doing on time? I'm doing all right. Okay, so let's say we have a short exact sequence of alinear maps of A modules here. So F and G are alinear maps. Kernel of, F is injective, G is surjective, and the image of F is equal to the kernel of G. Okay, so if that holds, then we have a short exact sequence where we just take everything and put S inverse on the end. So again, this is sort of an example of S inverse making things look really nice, or keeping things really nice. Like, if you have a short exact sequence here, you can literally just put S inverse on, in front of everything here, and you still get a short exact sequence. And so when I say so is this, what I mean is so is this a short exact sequence of S inverse A modules. So these are A modules, these are S inverse A modules, these are A linear maps, these are S inverse A linear maps. All right, so let's prove it. We got to prove three things. The kernel of, so we need this to be injective, i.e. the kernel of this map is 0. We need this to be surjective, i.e. the image of this map is all of S inverse M3. And we need the image of S inverse F to be equal to the kernel of S inverse G. So let's start with one of them, proving that the kernel of S inverse F is 0. So suppose you have an M1 over S in S inverse M, which is in the kernel, meaning that if you apply S inverse F to it, you get 0. Well, that means F of M1 over S equals 0. But you could write F of M1 as S over 1 times F M1 over S. And this thing is 0, so this product is 0. And so F of M1 is 0, which means that M1 is in the kernel of F. But we know that the kernel of F is 0 since this is a short exact sequence. And so if M1 is 0, then M1 over S is 0 as well in the ring S inverse M1. Because in the ring of fractions, 0 divided by anything is 0. So, or equivalent to 0. It belongs to the equivalence class of 0. Okay, so if M1 over S is 0, then it's in... So if you have something that's in... if you have something that's in the kernel of S inverse F, then it's 0. So the kernel is equal to 0. Okay, so to prove that S inverse G is surjective, take an element M3 over S, which is in S inverse capital M3. We know that G is surjective, so there is some M2 such that G of M2 equals M3. And you just take M2 and divide it by S and see what happens. M2 over S, it's certainly going to be an S inverse M2. And if you feed it through S inverse G, then you're just going to get G of M2 over S, which is M3 over S. And so we found an element in S inverse M2 whose image under S inverse G is precisely this element. And since this holds for every element in S inverse M3, we can conclude that the image of S inverse G is all of S inverse M3. All right. Lastly, we want to prove that the kernel of S inverse G is the image of S inverse F, and I lied. I said there are 3 things to prove. There's really 4, because this is 2 things. So, unfortunately, this problem wants us to do 2 things, but let's go ahead and do them. So, the first inclusion is we want to go image is contained in the kernel, so take something in the image of S inverse F. So let's take S inverse F of M1 over S, because that's what things in the image look like. It's just the image under this. Okay, so if we take this composition of maps and we feed M1 over S through this composition, then what happens is things happen in the numerator. The numerator just becomes G composed with F of M1 over S, but because this is a short exact sequence, anything that goes through F and then through G is 0, because the kernel of G is the image of F, and this is the image, F of M1 is in the image of F, obviously, so feeding it through G kills it. So this is 0 over S, which is 0, and so if you take this element in the image, then this element mapped under S inverse G is 0. So this element, which is in the image of S inverse F, is also in the kernel of S inverse G, because S inverse G kills it. So the image of S inverse F is contained in the kernel of S inverse G. Then for the other direction, you take something in the kernel of S inverse G. We'll call it M2 over S. Of course, this is because M2 is in capital M2 and S is in S. Okay, so if this is in the kernel, then G of M2, okay, where am I going with this? We can write this, certainly we just take S over 1 times G of M2 over S. G of M2 over S, well, G of M2 over S, that's just S inverse G of M2 over S. But we've assumed that M2 over S is in the kernel of this map, and so this is just S over 1 times 0, which is 0. So G of M2 equals 0, which means that M2 is in the kernel of G. But because this is a short exact sequence here, the kernel of G is the image of F. So M2 is in the image of F, meaning that there is some M1 in capital M1, which will map under F to M2. And so then we have M2 over S is equal to F of M1 over S, which is just the image under S inverse F of M1 over S. And clearly this is in the image of S inverse F. So therefore, anything in the kernel of S inverse G is in the image of S inverse F. So we have this containment, and so we have containment in both directions, and therefore the kernel of S inverse G is equal to the image of S inverse F. And that proves this direction. So a natural thing to ask is, can you go backwards? If you have a short exact sequence here, then you get a short exact sequence here. And I don't think this is proven in the lectures. I think this is I think there's a homework exercise that says that if this works for every single set S of the form A set minus M, where M is any maximal ideal. So if we get a short exact sequence here for every single S of the form A set minus M, where M is a maximal ideal of A, then you can conclude that that this is a short exact sequence. And in fact, in this scenario, it's an if and only if, because certainly if this is a short exact sequence, then we've just proven that this will be a short exact sequence for every single S of the form A set minus M, where M is a maximal ideal of A. But yeah, so in that scenario, you can go backwards, but that's something for another time. For now, we have this fact, and that finishes our discussion of this topic.